Physiology of excitation. Excitation is the property of the excitable tissues. Excitable tissues are nervous, muscle tissue, muscular tissue, and the secretory cells of or glandular tissue. Excitation definition is the change of the membrane potential of the cell in response to the stimulation. The membrane potential changes from the negative charge, approximately minus 70 millivolts. Then cell is stimulated and the membrane potential becomes positive, about plus 20 millivolts. The potential that may be measured by microelectrode or by electrode technique when electrode is introduced into the cell and then the voltmeter is applied, then the potential that is measured at the resting state is called resting membrane potential or RMP. We characterized already this resting membrane potential and told that it is about minus 70, minus 80 millivolts. How this resting membrane potential is explained? The cellular membrane consists basically of two layers of phospholipids. Phospholipids consist of the polar or hydrophilic head and non-polar or hydrophobic tails, and we have two layers. Such membrane is relatively impermeable for water, ions, etc. To transport ions, the proteins are needed. For example, ion channels. Proteins. For example, ion channels. They have the channel inside that is filled with water. And therefore ions can easily pass such ion channels. Another transport protein is called pump. For example, sodium-potassium pump. This pump may move or transport ions, but across the concentration gradient. For example, this sodium-potassium pump, utilizing the energy of ATP, moves potassium inside the cell and it moves sodium outside. This is outer and this is intercellular space. So channels, they transport ions following the concentration gradient from higher concentration to low concentration, pump against concentration gradient. So, saying that once more, sodium-potassium pump moves sodium from the cell and it moves potassium into the cell. But we have opened potassium channels. So potassium moves from the cell. It has positive charge, and therefore we have positive charge outside and relatively minus 70 millivolts in the cell. This is the explanation of the resting membrane potential. Again, sodium-potassium pump and secondary opened potassium channels. What happens when the cell is stimulated? If this is excitable cell, then stimulus activates sodium channels. Sodium channels may be divided in accordance with the control of their state. They may be classified as chemically regulated channels. They are opened or closed by hormones, by neurotransmitters, by drugs, etc. Also, we have mechanically controlled channels. And also we have potentially dependent channels. Potentially dependent or electrically controlled channels. They are activated by the charge, by electric current. So depending on what kind of stimulation we apply, we will activate certain sodium channels, and sodium will enter the cell, because I will remind, sodium is extracellular ion. Sodium has positive charge, and therefore it will change minus inside to plus, and this is called depolarization of the cellular membrane. Depolarization. After depolarization, the cell goes back to resting membrane potential, and it is called repolarization. Repolarization is explained by the additional amount of potassium that leaks from the cell, that goes out in accordance with concentration gradient. And some extra amount of potassium is leaving the cell, and for a short period the cell becomes even more negative than in the resting state, and this is called hyperpolarization. We may draw the change of the membrane potential in the time course of depolarization on the graph, and this graph is called. Now we will speak about the action potential. So we will draw the system of axes, abscissa and ordinate. On the axis, on the abscissa axis, we will indicate time. On the ordinate axis, voltage in millivolts. The initial potential of the resting state is minus 70 millivolt. When the cell is stimulated, we will indicate the stimulation by an arrow. We have the increase of the potential due to the input, due to the enter of sodium ions into the cell. We call this potential local response. This slight increase of potential, if the stimulation reaches the threshold, will reach the firing level or the critical level of depolarization. So here about minus 50, minus 55 millivolts, we indicate firing level or critical level of depolarization. At that level of potential, potentially dependent sodium channels open and sodium enters the cell like an avalanche. Huge amount of sodium is entering the cell, inducing the depolarization of the cellular membrane. When the highest potential plus 30 is reached, sodium channels close and depolarization occurs. First, a rapid depolarization and then slow depolarization. And we also may indicate the part of the graph that reflects hyperpolarization from minus 70 to minus 80. So here we have an action potential, and we can call the parts of this graph. A, pre-spike. B, spike, ascending and descending part of the spike. From this point to this point, we have negative trace potential, and from this point to this point we have positive trace potential. The excitability of the cell is reflected by the magnitude of the threshold stimulation. The threshold stimulation is the minimal strength of stimulation that is able to induce excitation or action potential. The more is threshold, the less is excitability. Excitability is not a constant parameter of the cell. It changes, for example, in the time course of the action potential. We will draw the graph that will indicate the change of excitability during the excitation. So, with the blue color, we will draw the change of excitability. Normal excitability 100% is increased during the local response, and also excitability increases during the pre-spike, because we go closer to the firing level at that moment. During the spike, excitability decreases and becomes zero for some period of time that is called refractory period. Excitability is absent. Then excitability increases gradually. This is called relative refractory period during the descending part of the spike, and you may see that during the trace potential the excitability increases. Meanwhile, we observe negative trace potential, and it is very important, excitability decreases during positive trace potential. This graph may be divided into the special parts that may be called: first, exaltation. Second, absolute refractory period. 3, relative refractory period. 4. Supernormal excitability. Supernormal. And 5. Subnormal. Subnormal excitability. Now we will discuss some laws of the excitable tissues. First is called all or none. All or none law. So this law states, in response to the threshold or over threshold stimulation, we get the maximal amplitude of the response. Action potential follows that law. Local response, for example, doesn't. Let's illustrate this law by the graph. We will measure the potential of the cell, and if we will use or apply the stimulus that is less than the threshold, we do not see action potential. Yes, we know we see local response, but it is not action potential. When we apply threshold stimulation, we see the action potential. When we increase the stimulation magnitude, we still have the same amplitude of action potential. Action potential will not increase. Amplitude will stay constant even if we will apply very strong stimulation. So again, we have maximal response if we apply threshold or over threshold stimulation. The next law is called the law of the strength time relationship. This law describes the relationship between the strength of the threshold stimulation and its duration. On the horizontal axis we have time, and on vertical axis we have the strength of stimulation, of threshold stimulation. This relationship is inverse. So we may see that if we produce the stimulation for a long time, then the strength decreases, the strength of the threshold stimulation, and vice versa. We may use the very short duration, but for that sake the strength of stimulation should be very intensive. The weakest possible strength of stimulation that still may excite the cell is called a rheobase. If we will apply the stimulation equal to two rheobases, then we will get a certain time that is called chronaxia. It was the second law, and the third law is the law of accommodation. The law of accommodation describes the intensity of the increase of the strength of the stimulation and the value of the threshold potential. For example, if we gradually increase the intensity of stimulation, then the tissue adapts to a certain extent to this impact, and the threshold potential will be high threshold. In comparison with a steep or rapid increase of the stimulation strength. So for effective stimulation, we should apply abrupt, rapid increase of the stimulation. Then the threshold will be low.